Um, who I am, Demetrius introduced me briefly. Yeah, I work at Databricks, been there for about 4 years. Used to be a data scientist. I've done a lot of stuff with personal projects that I've done in my career at companies, but also over the last 4 years have helped countless companies try to make sense out of data engineering, data science, and feature stores, actually, which is one of the reasons that we're going to be talking about today. And we're going to do this talk. I'm going to present a thesis, which is kind of ridiculous. There's going to be a lot of text that are going to be on these slides. You can review them later if you want to read through them, but they're meant to be funny. So our thesis is we're going to an ML project developed with entirely self-contained feature engineering, which is usually what we have with pipelines, isolates incredibly useful work within its pipeline and within that deployed production pipeline. An island is isolated from other parts of land because it's an island and it's surrounded by water. So we should build our ML infrastructure more like Tennessee. Now, this might get a little bit strange, but we'll go through this thesis and explain why I'm talking about it in this way. So this is Hawaii. It's an island, and there's a lot of really cool stuff there. Like really cool stuff. It's a great place to visit, but it's really known for being kind of hard to get to. It's pretty far away, and you can't really drive there. But people do go there, typically on ships or airplanes. And we also move cargo to there via ships and airplanes. Now, this is Tennessee. Tennessee is, from what I understand, it's not an island. And there's a lot of cool stuff there, I think. I've been there a couple of times, but can't really validate much of that. But one of the things that Tennessee is also known for, and it's not a particularly well-known fun fact, but it has the highest concentration of extremely large warehouses on the planet. And there's a reason for that. And it's because it's pretty easy to get there, sort of centrally located in North America. And it's really easy to get things to and from there. You can use things like trains, which are really hard, from what I understand, to go over the Pacific Ocean to get to Hawaii. And you can fly stuff there as well, but it's kind of expensive to fly things there. So that's it for the analogy so far. But what I wanted to bring this up for is because a lot of ML projects and things that we do with data are kind of like being on an island. The data science team / ML team is at many companies is sort of isolated as if it's in Hawaii, and getting requirements can be like we're receiving messages in a bottle cast off from the mainland saying, hey, data science team, we need this solved. Can you just go and do this? So that insulated aspect of work means that a lot of the feature engineering that's done is done separate from the data engineering team. That could be because hypothesis that we're trying to vet in utilizing for an application, the data could be incredibly challenging to get, very expensive, and it's just time consuming to write all that ETL. And because these ML projects are kind of like an island, and actually more like an archipelago, each project could be its own island that you may not be using or defining the exact same features that your peer is who's working on a different project. It may be that you're trying to use the same data in the same manner and doing the same calculations, but it doesn't actually turn out to be that way. So in this use case that I have on the slide here, this actually is a real world thing. The metrics that I'm going to show in the next slide are not real, but this actually happened at a company that I worked at before. We had about a dozen different products in the ML team and throughout BI, where we were all using the profit feature, and everybody had a different definition for it. Nobody was using what finance was using because it just wasn't in the data warehouse. So each of these projects calculated in a different way, and we end up getting these radically different numbers, and we're using these numbers in models. So when we start doing one of the most important aspects of productionizing our ML models which is attribution analysis and evaluating how much business impact our work is actually having, there's no way that we could actually do that accurately. And one of the reasons why this is so challenging is because in an ML pipeline, a lot of the infrastructure and frameworks that we use actually force us to embed this transformation logic within a pipeline, deploy it to production, hope that everything goes well, collect data that we can, but it's really hard for other projects to use that code without introducing incredible complexity to other projects. And yes, we can create a framework for this. We can build abstraction on top of data transformation tasks, and we can maintain and own a ton of infrastructure. It always sounds like a good idea when people start out doing that, and then you have to maintain it. And as it grows over time, you end up with buyer's remorse, and you really wish that you hadn't done that. I've actually lived through that. It's pretty painful. But this infrastructure that you build with a custom framework, all you're doing is just bridging. So you're making it so that it's easy for project A to access some transformation that project C built, and then cobble all of this together. But it's not truly a centralized resource of persisted data and an online component associated with that. Now, one thing that we always talk about, anytime that somebody's talking from a vendor, we always see this chart. So I figured I'd put it in this presentation. These numbers are totally made up. I just have seen this particular pie chart probably 1,000 times on different blog posts and in presentations. So I figured I'd do my own. But really, the messaging of what this is we spend a lot of time as data scientists and ML engineers with data, manipulating it, transforming it, doing things with it to solve a problem, throwing it away. There's a lot of things that we spend time on just getting a feature vector ready for an ML algorithm or creating a feature data set that we can use for analytics or statistical inference. And because our time is spent so much on that part of ML engineering, we don't have a lot of time for that other phase. So let's pretend that we are actually doing an ML project. We spent a bunch of months on creating this evaluation of whether a user is going to click on an ad or not. And part of this framework that we need to create for solving this problem, we need to do some point in time joins, which are kind of tricky to write yourself manually. But part of this join is taking a bunch of information about ads and about users, and then we're getting a stream of data coming in saying, did they click on the ad or not? So we need this data that's coalesced in order for not only for training to happen, but also at inference time. So this is kind of the feature store model. But what we ended up doing in isolation, because we're all living in Hawaii doing this, we created an ML pipeline that compartmentalized all of this data manipulation into its pipeline. And inevitably, anybody that's been doing data science for a while, you're going to have an executive at some point saying, hey, how much money is this making us? And the response to that, unfortunately for our use case here, is we just had an intern start. Chris, welcome to the team. And his first task that's given is to answer this problem. And after looking through how to actually solve this and digging through the data and realizing that I actually need the data from the pipeline, I need that logic from within that project. And what Chris doesn't know, what the rest of the team knows, is that it was a massive undertaking to create that pipeline in the first place and to write all that feature engineering code. And they were doing a large construction project effectively in code. And unfortunately, Chris is kind of set up like this. It's not really well equipped to go through all of that code. And what he ends up having to do is realizing that he's not in Hawaii with the rest of the team. He's over in Guam. And he's even further from where any of the data is and any of the core attributes that he needs to collect in order to answer this business problem. So he ends up reverse engineering everything that they built. He has to learn a new language. It's all written in Scala on Spark. And then he has to rewrite basically that logic in SQL and use a bunch of tools to do that analysis to say, it is creating this percentage of lift with this. And this is what my analysis of the A/B tests have shown. So we can use a feature store instead, which is basically like Tennessee. Now, for this use case that we're going through, that streaming data that's coming in, the raw clickstream data, we have an impression datetime. This is something that will be used for that point in time join, because the ad is shown at some particular time. We want to know what whether somebody has clicked on it and what the state of the user data and the click data was at that time that the impression was shown. So we have this information about ads, and what the relevance is to particular categories. And then we have data about our users, which is a slowly changing dimension. It's getting merged and updated periodically throughout the day as people are interacting with the platform. So what we could do is we can create in the Databricks feature store, we can create a feature table. We'll name it based on the database and table name. And we're going to give it the actual construction logic as that data frame. So whatever code we had to write in order to get data from sources and materialize something in memory, we can register that in the feature store, and it will allow us to periodically update it. We can schedule that to just update asynchronously, and we can also publish to an online feature store as well. And when we want to create this full data set that emulates a particular pipeline utilization of this data to solve this use case, we define it by saying these are the tables that we're going to be using to satisfy this join for basically the offline static data or the slowly changing data. And then we're also going to join it to the raw clickstream data, which is at the bottom here. And we want to use it for training. We just load the data frame. We want to use it for analysis. That last line of code in there is the same thing we're going to use. And that'll generate and materialize that data set for any use case that we need. So the TL and DR of this entire analogy that I've been talking about is this slide. And what a feature store that is fully integrated into an analytics platform can give you, and why it's so important. Because that operationalizing, remember back to the pie chart that we were showing, that little sliver of information that most projects don't get enough time to devote to that, or you do it post hoc, like well after it's already in production, you're scrambling to get everything going. It's a lot of rework that you'd have to do without a feature store, and enabling stuff like drift monitoring of your features, doing analysis of correlation for, hey, the model is predicting this thing. I need to know what features are driving that. And I need to know how to actually change reality in order to get better results in the future. And general model explainability for launching something that's going into the hands of customers. That's something that we really want to understand why that model is behaving the way it is. And then all of the reporting and analysis. When we were talking about attribution modeling earlier, being able to tell on anything that we're releasing to the business why it works is very important, but the business really cares about how much money is this making us, whether that's in cost savings due to it's efficiently automating something that the business is otherwise spending a lot of time on, or it's just directly driving sales. Being able to give that number in a very rapid way and analyze the state of the data going in and coming out of the model is incredibly critical. So to wrap up the analogy, if we're talking about this Tennessee location of data, it really is just roads leading to there. And if our ML project that we're talking about is in North Carolina, we can do that attribution modeling and BI analysis relatively easily, because we're all just pointing to that centralized, location of warehouse. And when we're doing inference, we're doing prediction, we're doing retraining, and just general analysis of the business in general, having that single source of truth that everybody can align on and say, this is where our data is. This is what we're all going to agree on is the state of the world. This just makes it that much simpler. So yeah, in conclusion, let's be more like Tennessee with using feature stores for not just model training and inference, but also for all of the other myriad activities that are around and surrounding productionized ML solutions. So a little bit of shameless promotion. If you want to check out more about Databricks Feature Store and all of the exciting features that we are currently releasing right now and stuff that's going to be on the roadmap over the next year or two, the team is working really hard and doing some great work. Check it out. Just search Databricks Feature Store. You'll find out a lot of information. And the other part of the shameless promotion, I did write a book on MLOps. And yes, there are dogs in it and a lot of jokes. Check it out. It's going to go into production, I think, in end of April, early May. The print copies will ship out. And thanks for having me. And if anybody has any questions, yeah, let's do it.